Hi everyone, this is Alan. This is our first tutorial session after the spring break. Before we start, I have some announcement. First, from now to the end of the semester, homework will not be collected and solutions will be distributed on Sakai, and there will be no second midterm, only final exam. And to help you better, I will hold office hour Tuesday, 6 p.m. to 7 p.m., Thursday, 2 p.m. to 3 p.m. Both are Eastern time. And this is my email address. If you have any questions, you can send the email to me. Let's first look at series method. Series is a way to represent functions. So if we have a function fx, in many circumstances, we can expand it like this, which is a summation of polynomial. And the important thing here is find out the coefficient. For example, we can expand exponential function like this, sine function like this, and cosine function like this. Both sides of the equation are equivalent. It's just a different way to describe the function. Meanwhile, we should notice that there are many functions that don't have a form of elementary function. One of the very famous examples is this. Fx equals to the integral of exponential of minus s squared. This function, we cannot write it in forms of elementary function. That is, we cannot write it as sine function, exponential function, or their composition, or some other elementary function. There is no way we can write it in such a form. And meanwhile, we should notice it is possible for us to write out a series representation of this function. So by showing this example, I want you to understand series method gives us more flexibility since it can cover an even larger range of function. And since some of solution to some of the equation don't have an elementary form, it is impossible for us to try to find out an elementary solution for those kinds of equation. Next, let's look at series solution. So series solution is by plugging the series form of the solution into the original equation and then find out the coefficient. Let's look at a simple example. Here, we want to solve this equation. The second order derivative of y minus 4 times y equals to 0. Clearly, it is a second order linear equation, and we have learned many ways to solve it before. For example, you can use y takes the form like this, e to the lambda times x, and plug in this to the original equation, we get this, and we can solve lambda equals to plus minus 2. And hence, we can get the general solution. What if we assume the y have another form, that is, it has a power series form like this, or to be more concise, write it as this. Our strategy to use this form is plugging y into the original equation and then find out the coefficient an. To find out the coefficient an, what we need to do is use this form to replace all terms that contains y in the original equation. Then what we need to do is first to replace this term y and this term, the second order derivative of y. Y, we have already get what it looks like, but for second order derivative, we need to calculate it as this. Since for this term, it is from 0 to infinity, the summation range, and here is from 2 to infinity. We can use a simple change of variable to find out another form of this summation. just look like this. And by doing so, we can combine them together more easily. 0 equals to second order derivative of y minus 4 times y. And if we combine them term by term, we will get a form look like this. By comparing the coefficient on both sides, we can find out a recursive relation, which is this. So since both sides should equals to 0 and xn is a independent variable, that means if we want to it have 0 all the time, it will require that each coefficient equals to 0. That is, it will have this recursive relationship. And we can use it iteratively. By using it iteratively, we can use it again and again, like an plus 2's relationship with an, and then an's relationship with an minus 2, and an minus 2's relationship with an minus 4, and so on, until we stop at the beginning value, initial value. For example, with this method, we can find out the explicit solution for an. It looks like this. When n is even, it has a form like this. When n is odd, it has a form like this. Here, a1 and a0 are independent constant. Since this is a second order linear equation, we know it has 2 independent constants. I have a few remarks about this method. First, we need to notice that by using this method, we in general will face more complicated calculation, and we should be more careful when we are using this method. Second, sometimes we cannot obtain the explicit formula for the an, but we can have a recursive relationship. For example, if we have a recursive relationship like this, it is a little bit hard for us to find out what the explicit formula for an look like. But in exam or in homework, it is enough for us just to write down the first few terms. For example, here we can assume an and a0 and a1 are independent constant, and then we try to calculate a2, a3, a4, which takes a form like this, and this respectively. And this is enough for us to have a big picture about what this coefficient looks like. And we don't need to write down the explicit formula for an all the time. And lastly, I want to re-emphasize that series method is a very powerful way to represent function. And sometimes the solution can't be written as composition of elementary function. That is, we cannot write function in the forms like this that are simple elementary function, or they are a composition, but we can find out a solution takes a form like this. Now let's look at Leibniz rules. Leibniz rules are used to calculate the higher order derivative. So if we have a product of two functions and we want to take the nth order of the derivative, we can use Leibniz rules like this. We can notice that these formula are quite similar to binomial expansion. The good thing of this formula is we can calculate the derivative of each element first and then combine them together. Let's look at an example. It is a homework problem. We want to take the 10th order derivative of x times e to the power of x. And here u is x, v is exponential function. And by the formula, we can write down the expansion, look like this. And we can notice that x can only have first order derivative with other derivative equals to 0. And exponential function is a very special function. No matter how many times you take derivative, it will still be the exponential function. Therefore, we can get a result look like this. Simplify it, we can have this. So this is everything for today. If you have any question about the homework or anything related to this course, you can send me an email. I will try to answer your question as soon as possible. if your questions are too complicated to answer by email, I will try to answer your question during the office hour. And the office hour link is on Sakai. Feel free to drop by, and thank you.